what's up there, which is -1. So it's going to wind up being a minus there. Maybe what I should have done, since I'm going to have to write it again, I'll write this one the way it would have happened had I done the derivative using chain rule. So that's derivative of e to the 2x itself times derivative of what's up here, which is 2. And then when I rewrite that, that's 2e to the 2x minus e to the -x. That's my derivative, right? I'd like to know where that's 0. I'd like to know where it doesn't exist. So let's start with where it's 0. Well, you have to set it equal to 0, right? And there's a couple of ways to do this. Not sure how you would do it, but maybe this will help. Can't bring the log in yet. If you wanted to try and kill off e, you can't do it yet because there's 2 e's. So how about I write it like this? Do you all agree this is the same thing? E to the -x is really 1 over e to the positive x. You're just dropping it down to the bottom. Now I did that because I'm going to now get a common denominator. Put these together. Is that fair? Okay. So if I get a common denominator here, I have to look at this as being over 1, right? I'm trying to get it as a fraction now because, remember, a fraction can only be 0 if the top is 0, right? So I'm trying to create this fraction. So I have to multiply the top and bottom over here by e to the x, top and bottom. And that'll give me the same denominator, e to the x. And then what happens when I multiply this? I'm multiplying all that together. You'll have a 2. How do you multiply e to the x times e to the 2x? What do you do to the exponents? You add them. So it's e to the 3x, right? E to the 3x. And then I still have next to it -1, and that's all over the common denominator. Right? Go ahead and put them together now. You all agree? Now that can only be 0, right, if the top is 0. So if I set the top equal to 0, 2e to the 3x minus 1 equals 0, I have to solve that equation for x. And so I'm going to try and treat it kind of like a linear equation. I'm going to isolate this by itself. So I'm going to add 1 to both sides. And once I add 1 to both sides, I will divide by 2. Is that all right? Move the 1 over, and then divide both sides of the equation by 2, you get this. Now you can bring in the natural log. Now you can. So I'm going to take the natural log of e to the 3x equals natural log of 1/2. What does the left-hand side become? 3x. The whole point of bringing in the natural log is to kill off the e. So we get 3x here, and then over here we have natural log of 1/2. And my final step to get x by itself is to divide both sides by 3. So I'll just put 1/3 natural log of 1/2. There we go. Dividing both sides by 3 is the same as multiplying both sides by 1/3. So that's the way I chose to write it. If you want to write it like this, you can write it like that. But that, to me, looks better. OK, is that a number? Yeah, I mean, I could figure out what that is. I need my calculator, but I could figure it out, right? So somebody get their calculator. Oh, by the way, does the derivative not exist? Does the derivative not exist? Well, this is not as straightforward, is it? I mean, it's not a polynomial. But you should know from college algebra that when it comes to exponential functions, there are no domain restrictions here. You can plug any number you want into this and any number you want into this. You're never going to have like division by 0 or anything. So we have no issues with this derivative at all. What is it? This comes out to be what? Approximately -0.231, somewhere around there. Now the reason I got that is because I have to put this on a number line, and then I have to figure out like a point to the left and to the right to test. And so I need to know what that number is so I have an idea of what to pick. Pardon? 3-1? Wait, say again?
Never mind. No.
It's negative?
0.231.
What were you saying about 0?
I was saying like it would be
As a test number.
Oh, okay, as a test point. Gotcha.
Yeah.
I thought you were saying I should write it like this. Right? That's the same thing, right? By the way, I never really ever put zeros in front of my decimals, but a lot of times textbooks do. And it's really because sometimes if you don't put the 0, you kind of like maybe might not see the decimal and you might actually think that's 231. And so books put zeros in there just because when you see the 0, that's like, when would you ever put a 0 in front of anything other than a decimal? You know what I mean? So, all right, so now I'm going to draw a number line. I'm going to put 1/3 natural log of a half on there, which we know is approximately negative 231, right? And that breaks my number line into 2 regions, and I need a test point in each region, right? So negative, what'd you say, -1? In 1? That's fine with me. I don't care. As long as it's to the left, I don't care what it is. So -1 would work, and then over here, +1. And it doesn't even have to be drawn to scale, okay? Just pick any number over here, any number over there, and where are these numbers getting plugged in?
Derivative.
To the derivative. All right, so I need to know what is the derivative at -1, and I need to know what is the derivative at +1. And the derivative, I erased it, didn't I? But I have it over here, don't I? Wasn't that the derivative? I was setting it equal to 0, right? But that's the derivative right there. When I put a common denominator, that's what it looks like, right? What can you tell me about this denominator? E to any power? Always what?
Positive.
Always positive, right? Think about the exponential function. Looks like that, right? E to any power is positive. So the denominator is positive always, right? Okay. So I need to figure out what happens when I plug -1 really into the top. So you're going to need to do this on your calculator. E to the -3, then multiply by 2, then subtract 1. You're getting a negative number, right? Yeah? You have to try on your calculator, but you should get a negative number there. So I'm not going to show this work because it's just algebra, right, and calculator. You should get a negative number here, which is less than 0, right? So over here, my derivative is less than 0, which tells me what about the original function? It's going down. Decreasing, right? Going down. All right, then I plug in 1. I plug 1 into this, and that number will be bigger than 0, so that'll be a positive number, which means it's positive, right? The derivative being positive means my original function's going up, right?
So if you plug in numbers into the derivative and you get 0.
No, I'm not.
No, but like if you do, then on the graph it's just going to be a horizontal line, right? We don't do any increasing or decreasing.
If I plug a number in and I get 0,
Right.
then I've messed up. Because I should never, that's what these points are, right? This is where the derivative is 0, right? This, remember we solved, we set it equal to 0? We set it equal to 0 and we solved and we got that answer. So this should be the only place that the derivative is 0. So if one of your test points gives you 0, you should be like, shit, I missed something over here. You know, it should either be positive or negative. That's it. Yeah, good question. All right, we're ready. That was weird. Right when you were drinking, he was doing that, and I thought that was coming from your cup. I was like, what the hell are you drinking?
Quick question.
Yeah.
On the simplification from 2e to the 3x minus 1 over e to the x, how do we lose the e to the x in the denominator?
Oh, remember that a fraction can only be 0 when the top is 0,
Okay.
right? So that's,
Gotcha.
yeah. All right, I'm ready to, I think I'm ready to put my answer. So for part A, where's this function increasing? Where is it increasing?
To the right of the critical point.
To the right of the, so that would be 1/3 natural log of a half, right? To infinity. Just, one mistake I see on the increasing, decreasing, is that when students tell me where it's increasing, they use this number. as in the interval. No, it's from here on it's increasing, right? And then it's decreasing where? Left of it, so negative infinity to that critical number, right? Part B, local max. Do we have a local max? No, we don't have one. None. Right? The graph never goes up, then back down. Question?
If there was a range given, would we have to notate none along this interval? Or do we just say none?
You just say there's none. There's none, yeah. Local minimum, do we have one?
Yes.
Yes. And this I want to write as a point. And this is going to suck because it happens the x-coordinate is 1/3 natural log of a half, right? And then the y-coordinate is what I get when I plug that into what? The original function. Or why don't we do the negative 0.231?
Can you
Yeah.
just say f of that point?
Well, we actually want to know how high it is. Or in this case, we actually do want to know how low it is. So we do want the actual value. Yeah. But I would say plug in negative 0.231 into that original function, which I've erased. But it's up there, right? But while you're doing that on your calculator, I'm just going to graph it because I'm curious to know what this looks like. I mean, we have a pretty good idea of what it looks like. Not a perfect idea, but a decent idea. Let's see, e to the 2x minus e to the negative x. What the heck? Was it plus or minus? It was plus in the middle? Okay, that's why I was like, what the? That doesn't look right. There we go, there's the graph. Almost looks like a parabola, but it's not. It's hard to see from this graph. Let me do this. It's hard to see from, well, yeah, you can see it this way. See that? Local minimum there? At negative 0.231, that's what we said. And then it comes out to be 1.8899. Let's just say 89. All right, you get the idea? So in your homework, really the challenge is going to be the same thing it was in 4.1, which was how are you doing taking your derivative and setting it equal to 0? How are you doing taking your derivative and figuring out where it's undefined? Once you have those numbers, your critical numbers, once you have those, then it's just a matter of a number line and test points, and none of that is like crazy algebra. It's just plugging numbers in, right? Understand? We've just added another layer to the critical number idea. Yes?
For the test, is there like a handwritten way we can find that y-coordinate, get the full point of the local minimum?
Yeah. The original function, right, was e to the 2x plus e to the negative x, right? So you would do on your calculator e to the 2 times negative 0.231 plus e to the negative 0.231. So you would have to be able to type that into your calculator.
And that'll give that
And that'll give the 1.89. Yeah. But just make sure you're plugging this into the original function. The only thing that ever gets plugged into the derivative are the test points. Everything else goes into the original function. All right. Let's talk about the second derivative. We know the first derivative tells us where a function goes up and down, right? We only have 20 minutes left, but we can knock this out. Right? The first derivative tells us where a function goes up or down. The second derivative tells us about something called concavity. Concavity.
How do you spell that?
I'm going to bring it up in the notes here. That's it right there, concavity. All right, so let me show you visually what it looks like. Can everyone see that okay? Let's kill the lights. Maybe not. Ooh, yeah. All right. So from this graph, you could tell me where it's going up and down, right? Increase and decrease. That we already know. Now what I'm going to do is I'm going to drag this thing across here. And what I'm doing is instead of looking at the first derivative, I'm looking at the second derivative, right? Which is a different function. And I'm figuring out whether or not it's positive or negative. So let me drag this across. Right now I'm telling you, you don't know why yet, but I'm telling you the second derivative right now is negative. And I'm going to keep dragging across. It's negative, negative, until I get to about right there. Then it changes to positive. Then it changes to negative. Then it changes to positive and stays positive the rest of the way. What the hell is concavity measuring? What is it? It's not the up and down, right?
It's the cup.
It's the what?
The cup.
The cup?
Oh yeah, is it cupping upwards or cupping down?
Is it like cupping up or down, right? Do y'all see that where it's red? Anywhere it's red, it looks like a frown of a smile. And anywhere it's green, it looks like part of a smile that's up. Wait, did I say frown of a smile? That's not what I meant to say. Does everyone see, like if you think about a smiley face and a frown, right? Smiley face, right? Frown, down. Okay? Concavity has to do with that. Concave up looks like that, concave down looks like this. So wherever you're red, do you see that we are concave down? Looks like part of a frown.
Yes.
But then in this little region is part of a smile, and then you're back to part of a frown, and then back to part of a smile, and then ignore that, that's not part of it, right? So the second derivative is all about frowns and smiles, or concavity. That's mathematically we call it concavity, we don't call it smiles and frowns, all right? But that's all it is visually for us. Smiles and frowns. So when the second derivative is positive, this is the same note that we just had for the first derivative. If a function, let me see, I want you to look at, I just want you to look at, this to me, we don't need to talk about 1 and 2. All right, we can just go to 3. If the second derivative is positive on an interval, then we are concave up. We look like a smile. If the second derivative is negative, it's concave down. It looks like a frown. That's easy to remember, right? Positive people smile, negative people are frowning all the time, right? So that's the way you think of concavity. But we're looking at the second derivative, not the first. Now, any point where we have a change in concavity will be called an inflection point. So you know, like for the first derivative, right? For the first derivative, when we're talking about f prime, right? When a graph goes up and down, that point there is a local max, right? And if we go down and we go up with the first derivative, that's a local minimum. When we're talking about the second derivative, we don't have that idea. We have an idea of a frown switching to a smile and a smile switching to a frown. And those points where it happens are called inflections. So going back to that picture, going to this picture, okay? If I look at that picture, I have how many inflection points? Anywhere it goes from a frown to a smile or a smile to a frown. So moving from left to right, 1, 2, 3. I have 3 inflection points. All right? So how do you think we're going to figure out where we have these changes? Yes?
When the derivative is either 1 or 0?
Where the derivative is either 1 or 0?
Yeah, because like you see like at the inflection points, like it kind of looks like that's when it's kind of weird to say, but like it starts changing. I don't really know how to word it because I don't know how to word this.
I think I can help you because I think I know what you're saying. All right, look at that graph right there. Do y'all see the inflection point?
Yeah.
Somewhere around here, right? Yes? That looks like where it goes from from smile, right, to frown. It's like where the 2 corners of the lip come together, right? The smile becomes the frown. I want you to look at back to the tangent line for a second. On this entire graph, the derivative here is what? Positive, right? You all agree? It's positive. Now, think about the steepness of this. Okay? What's happening right now? It's becoming steeper, 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 right? So the derivative is getting bigger, right? And then you get to this point, and what happens? The derivative starts to get smaller, right? So the inflection point is where the derivative goes and has like a max or a little maximum. I think that may be what you were talking about. It's like where something happens. Okay, got it? So let's go back to the problem we started with, the first problem we did. Remember this one, f of x was x cubed minus 6x squared, right? We figured out where that graph was going up and down. We found the local max and local mins, right? That was the graph, wasn't it?
Yeah.
Or that was the function? Okay, what I'd like to do now is add some things to this. We did part A and part B, right? I'd like to add to this now. I would like to know, I want to find where f is concave up, and then where it's concave down. And then part D, I want to find any inflection points. I have good news. We're going to do the exact same thing we just did, but we're going to be looking at the second derivative, not the first derivative. So we already took the first derivative earlier, right? The first derivative was 3x squared minus 12x, right? That was our first derivative. Now, let's go look at the second derivative, because second derivative tells us about the concavity, the smile and the frown. So the second derivative of this function is going to be 6x minus 12, right? 6x minus 12.
Yeah.
And now what I'm going to do is I'm going to do the same thing we did with the first derivative. I'm going to find where's the second derivative equal to 0. And I'm going to figure out where's the second derivative not exist. And then whatever I get, I'm going to put them on a number line, and I'm going to do a test point, just like we did with the first derivative. Our conclusion is going to be slightly different, though. Our conclusion is not going to be, oh, this is where our function goes up and down. It's going to be, oh, this is where we have frowning and smiling happening. So where's the second derivative? 0. Set it equal to 0. X is 2, right? Add 12, divide by 6. Does this ever not exist? No. So no problems here, right? Any questions? Now what I'm going to do is I'm going to draw a number line. Put my critical number here, 2. That creates a natural partition of the number line into 2 regions. I'm going to pick any test point I want in these regions. So what do you say? 1 and 3, okay, 1 and 3. And where am I going to plug those points in? Where am I plugging those x values to? Second derivative. Test points always go into derivatives. And since we're talking about concavity, these are going to go into the second derivative. So I want second derivative at 1, second derivative at 3. So second derivative is right here, right? What happens when you plug 1 in there? You get a negative number, right? So I get a negative number. Okay, that means over here at 1, why did I put that down at 3? I have no idea why I put that down there at 3. That's at 1. I get a negative number, which, right? So that means that the second derivative over here is negative. And since we're talking about second derivative, we're talking about happy and sad people, right? And negative people frown, right? So this is going to be concave down. So my original function over here, remember for increase and decrease, I used an arrow up and down. For concave, I do this, a little frown like that. So the second derivative over here is negative, which means my original function is frowning here. Now we plug in 3. We get a positive number. Right? It is positive or no? Yeah, it is. Okay. So we get that. That means the second derivative there is positive, and second derivatives tell me about smiling and frowning. So positive people smile. So I know my graph must look like that. Okay. Part A, or part C, sorry, part C. Where is the function, let's start with concave up. Where is the function concave up? 2 to infinity, right? Where is the function concave down? To the left of 2, right? So negative infinity to 2. And finally, part D, do I have any inflection points? Do I have a point where I have a change in concavity? I either go from frown to smile or smile to frown? Yeah, frown to smile, right? It happens at 2. So what I'm going to do is I'm going to look at this as a point. And it's a point on the graph of the original function. So I need to go back to the original function and plug 2 into that. 8 minus 24? Yeah, 8 minus 24. What is that? Negative 16? Okay, negative 16. Go back to Desmos. I think I still have that graph there. There it is. I'm going to graph that point, 2, negative 16, right there. That look like the inflection point to you? Yeah? Looks like it to me. To the left of that point, I'm concave down. To the right of that point, I'm concave up, right? So do you all see the difference between concavity and, second derivative concavity versus first derivative increase, decrease? They give you two different things, right? They're talking about two different aspects of the graph. Okay, let's see here. There's one more thing I want to talk about. It's kind of on topic, off topic. I don't have enough time to do another problem. We only have 6 minutes. But I just think this is a funny story. So I used to have this colleague that I used to work with when I first started teaching here. And I don't know how to say this nicely. In fact, I'll mute myself.